Okay. Hello, everyone. This is the fourth in a series of lectures covering Chapter 5. We're going to talk about the relationship between uniform circular motion and simple harmonic motion. To put this into a real-world example, consider the classic sewing machine, not powered by electricity, but by a foot pedal. By essentially gliding the foot pedal back and forth, you will start spinning a metal wheel that will drive the sewing needle. So there seems to be a connection then between the rocking motion you're doing on the foot pedal and the circular motion of the wheel. It will appear to be then that simple harmonic motion and uniform circular motion are related. In fact, you can think of simple harmonic motion as the shadow of uniform circular motion if it's projected on a single axis. So to make that example a bit more clear, imagine that you have a ball attached to the rim of a turntable, and this turntable is kind of picked up and flipped on its side so that the top part of the turntable is now facing you, and there's kind of like a ball attached to the rim there, and it's rotating. So it kind of rotates like a needle of a clock. In this case, though, it's rotating counterclockwise, and the lamp above it is casting a shadow on a screen underneath. So as the particle rotates counterclockwise, I mean, you will see the shadow moving on the screen. It turns out, though, that the movement of the shadow, which is just going to be moving left and right in a single line, can actually be described with simple harmonic motion. So I'm going to get into that, and for the purposes of exercises and examinations, this bit is a bit supplemental, so it's not something that you'll have to derive yourself. It's just an explanation of how the two are connected. So consider a circle with a radius equal to a. So again, that's just some constant, and there's a particle right at the circumference of the circle at point P, and this particle is going to move counterclockwise. But at the starting point, at the starting line, we're at point P, and this particle makes an angle equal to phi with the x-axis. So over time, as this particle rotates, as this particle moves through the circle, its angle then will shift. And if the angular speed of this particle is omega, you can always calculate the current position of the particle by taking the initial angle phi and adding to it omega times the amount of time that has passed. So this is kind of like x is equal to, vt times initial position x naught we've seen in kinematics. Meanwhile, though, if you look at the graphs below, consider the projection of point B on the x-axis. So that's shown as point Q in graph B, C, and D. And the idea is that we can always find the projection of P on the x-axis, which is, the projection will be right here. And because the particle is moving counterclockwise, starting off then, the projection will be moving to the left, as shown in graph C. And likewise, if you think then, okay, the horizontal displacement of particle P is to the left, likewise, the speed of point B being a uniform circular motion is tangential, as shown in graph C. So you can find a horizontal component of that speed, which is actually then the speed at which the shadow that it casts on the x-axis, point Q, moves along the x-axis. And the same thing with the centripetal acceleration that again points along the radius to the center of the circle. That one also has a horizontal component that can be used to describe the acceleration of point Q along the x-axis. So the particle P, as it moves through the circle, you can always talk about its projection along the x-axis by basically taking the radius times the cos function as a product of the angle you're currently at, right? So remember that omega t plus phi is the current angle after some amount of time has passed, accounting for the initial position phi. So you can always use, the cos function, because after all, at any point, right, particle P makes an angle of theta. So the x component being the adjacent side, then the cos function would give you the hypotenuse, the adjacent side or the hypotenuse, which is in this case the radius. So you get a formula for x, and because we know that theta is a function of the angular frequency and phi, we end up with the formula here on top. So then the sort of the shadow of particle P on the x-axis can be described with this cosine formula, which is the exact same displacement that a oscillator in simple harmonic motion has. So as the particle moves around the circle, its projection is moving in simple harmonic motion across the x-axis. So there's a few more observations to make. I don't want to spend too much time on them, but essentially, after one full period, one full cycle, point P has returned to its starting angle phi. It's made a full lap around the circle. And in that time, then the shadow has also returned to its starting position at point Q. Now, when comparing the movement of the shadow, which is a harmonic oscillator, with the speed of the point P moving along the circle, turns out that the angular frequency are equivalent. And also the phase constant is also equivalent. So whatever angle point P starts at when it starts moving in circles, that's going to be the phase shift for the shadow. And also the amplitude of oscillations is going to be the radius of the circle. So a bit more discussion here, but essentially you can get the velocity of the shadow if you look at the velocity vector of the particle and take the horizontal component, and you can do the same thing with the tangential acceleration and get the horizontal component of that. And you'll see by deriving that again using trigonometry, using cos and sine, that the acceleration and velocity, this horizontal component, is exactly that of a harmonic oscillator. So the horizontal projection of a particle moving in uniform circular motion is exactly a simple harmonic oscillator moving about the x-axis with a radius with an amplitude equal to the radius of the circle and an angular frequency equal to the angular frequency of the particle P. So a bit of a quick quiz here. We have the turntable experiment we talked about earlier, and we know the radius is half meter. Initially, the ball is located on the left side of the turntable, so the ball actually starts right over here, all the way on the left. And we're asked to find the amplitude and phase constant for the simple harmonic oscillation motion of the shadow. So you can imagine that starting off at t equals 0, the shadow is right here, and eventually start, as the particle moves, then the shadow that gets cast will move right and left. And what we know is that the radius is half a meter, and we know that the radius also sets the amplitude for the oscillations of the shadow. So that will be 0.5 meters for the amplitude. And that means we can't have B or DS answers. And we also need to know the phase constant. Now remember that the phase constant for the shadow is equal to the initial angle of the circle. And initial angle, we say we start all the way to the left. So initially, always measuring the angle from the positive x-axis, we start off at 180 degrees, or in radians, that'd be pi. We generally default to radians when we work with these equations. So our answer would be C. We're going to talk about the pendulum now, and the pendulum isn't a simple harmonic oscillator by default. So the idea is that a pendulum, the bob of it, swings in an arc. And then if we wanted to model its motion, its displacement, it wouldn't be accurate enough to talk about, say, it's just horizontal or vertical displacement. We'd like to talk about the way it traces an arc throughout its motion. And really, the arc is related to the angle, the angle that it covers through the motion. So we want to be able to talk about the angle that the pendulum traces over time. Now, the way the pendulum works is that the beam connecting it to a hinge or a ceiling, like or the rest of, say, a grandfather clock, that provides a tension that counteracts the weight of the bob, and there's always a component of the weight of the bob, mg, that's always actually perpendicular to the tension on the string. And this component, that being perpendicular to the tension and also to there's a component of the weight of the bob that is perpendicular to the tension, and with some trigonometry, that component is mg sine theta. So we also know that the total length of the stick is a length of L, and the idea is that as the pendulum swings farther and further to the right, this tangential component mg sine theta increases because the angle gets bigger. And the only thing is, though, that as you can see, the pendulum, as it swings to the right, the weight of it, this component of the weight mg sine theta, wants to make it fall and swing to the left. So there's a restoring force here that's always trying to push the pendulum the other way than where it's swinging. So as it swings to the right, the restoring force wants to make it go left. And the farther it swings, the stronger the restoring force. So then the restoring force then is mg sine theta with a negative sign to indicate it's always going the other way of the angular displacement. And by Newton's second law, we can write that as the mass times acceleration. Now, the acceleration is along the arc traced by the pendulum, so it's a derivative of s, which is the arc length. Now, the arc length can be calculated as whatever angle, whichever angle at pardon me, a bit of a tongue twister. At whichever angle the pendulum is currently at from equilibrium, you can calculate its current arc length by the product of the length of the pendulum times the angle. So this formula, using second Newton law, can be rewritten as a formula for the second derivative of the angle. And what we get then is that essentially the acceleration of theta is related to GL and sine of theta. So this does kind of look like simple harmonic motion, where the acceleration of a spring block system was proportional to its displacement. The only difference, though, is that the acceleration for this pendulum is proportional to sine of theta, which isn't quite simple harmonic motion because that's not directly proportional to displacement, but for small angles, the sine function is actually approximately equal to theta. So, like sine of 1 is really close to just 1. So overall, the rule of thumb is that if the pendulum is swinging with an angular amplitude of less than 10 degrees, then it's fair to approximate the sine theta to theta. And then that leaves us with a relationship between the angular acceleration and theta. So now we have that the angular acceleration, the magnitude is proportional to theta, but it's in the opposite direction. So this is simple harmonic motion. And as long as we can do this small angular approximation, as long as it's a small arc that it swings through less than 10 degrees, then we can treat the pendulum as a simple harmonic oscillator. Note though that if you look at the last slide, the way that we defined the angular frequency for the spring was by taking the terms in front of x and just calling that our omega, or angular frequency. Now, we're not dealing with a spring anymore. We now have this other constant terms for the pendulum, which we'll use to define our angular frequency term. So if you go back to your Newton's second law with a small angle approximation, you can solve the second derivative of theta and get a formula for the angular displacement of theta from its equilibrium position. And when we talk about the equilibrium position of a pendulum, that's just when the pendulum's perfectly vertical. And the formula then looks a lot like the one we've seen for the mass spring system, but instead of a max amplitude, we now have a max angular displacement. And we have a term again for angular frequency that's measured a bit differently. And we still have a phase shift to account for the starting conditions of the pendulum. So then the pendulum swings left and right. We can talk about its period and its rate of oscillations. How long does it take to swing through a full arc? And since the angular frequency is related to the period, like we've seen in the other harmonic oscillators, we can calculate the period if we know the length of the pendulum and the gravity. In other words, the longer the pendulum is, the longer its period, regardless of its starting angular amplitude. And again, period is just however long it takes to complete a full cycle. So how long it takes to swing out and come back. And likewise, you can talk about the frequency, which is, how many cycles you can do in unit time. And that's always going to be the same definition. The relationship between period and frequency in all units is always one's the reciprocal of the other. So yeah, so a note here, like I said, this only depends on L and G, not on phi or T. So let's look at the Grandfather clock here. And obviously, it has to swing with exact same period so that the hands of the clock tick evenly every second. Now, some child slides above down the rod, so it's a bit further along, closer to the floor. And the question is, well, what happens to the grandfather clock? So basically, the grandfather clock, has a certain fixed period, which we know is proportional to the square root of the length of the pendulum and the gravity, the gravitational constant. What's happening in this question is that the child has essentially made the pendulum longer. So basically, the length of the pendulum has increased, and because there's a proportion between the period and the length, then the period also increases. And if that is true, then a longer period means that the bob of the pendulum takes longer to make a full cycle. Then the grandfather clock will run slowly as it takes longer to tick. Question 2 asks, what if the grandfather clock is calibrated correctly at sea level and then it's taken to a mountaintop? So if you remember this from maybe mechanics, that the closer you're to the Earth, the stronger the gravity is. And at the mountaintop, then the gravitational acceleration to the gravity is lesser. And you're going to the mountaintop where there's less gravity, and the relationship between the period and gravity is inverse, right? So if the gravitational value is decreasing due to the inverse relationship, the period increases. So it takes longer to tick, which means that the hands tick slowly, and therefore the grandfather clock runs slowly. That's it for this lecture. Join me back for lecture number 5.